Today we're going to discuss the common ion effect. I'd like you to turn to worksheet 21 in your packet. I want you to consider the following reaction. This is our hydrofluoric acid, and it's splitting apart into hydrogen and fluorine. And the question that we need to answer says, initially in solution, what will take place when we add the HF? Well, if we put HF into solution, initially our HF dissociates to form some H plus and some F minus. But it's important to remember that the HF remains, that not all of it splits apart. If it was a strong acid, we would see almost all of that split apart, but in fact it's a weak acid, and so quite a few HFs will stay together. And so the next question says, what would happen, we want to think in terms of Le Chatelier, what would happen if we were to add F minus or H plus to the reaction? Which way would the equilibrium shift? Well, this is best visualized by looking right at the reaction here. So if we were to add F minus or H plus to the reaction, and it wouldn't matter which one because they're on the same side of the reaction, but I'm going to pick F minus because that's ultimately where we're going to end up adding. If we were to add F minus, remember, anything that I add, my reaction is going to shift away from. So it'll shift this direction, which means more of these will come back together to form more HF, and my concentration of H plus will go down, so it'll become less acidic. The shift is called the common ion effect. We are adding more of one of the ions already in solution. Makes the solution less acidic by inhibiting the HF from dissociating. This will alter our pH. However, all of our steps for solving these problems are still the same, which is really good. So, looking at this first problem here is a practice problem. And this is just a regular weak acid, okay? So this problem here is just a weak acid. We'll call it WA for weak acid. So I'd like you to do that problem first to figure out what the pH is, and then you can see that indeed when we do add a common ion, it's going to make this less acidic. So pause the video, go ahead and do worksheet 22 as practice. Okay, let's take a quick look at this practice problem that you did on your own. Your major species is acetic acid. You chose which species can dominate by writing the K values. There's only one, 1.8 times 10 to the minus 5. The initial concentration is 0.2. I'm starting to skip out steps as we start to condense things. So you need to always remember to write the equilibrium expression. It's definitely going to be points on your test. So it didn't ask us for it anywhere, so I just went ahead and did it. It said to do our ice chart, so I went ahead and filled it in. 0.2, 0, 0, minus x, plus x, 0.2 minus x, x and x. And then I went right to checking the 5% rule. Obviously, we need to solve the problem. So I went ahead and substituted back into our equilibrium expression. Since I had it written up above here, it was okay to just go ahead and substitute it in. I'm just going to cross out this X. I don't need to recopy it. It's okay to cross it out, but we can't like scribble the whole thing out so we can't see it. We just very lightly circle it and give it a single slash through, indicating that we're not using that X in our calculations. We solve for the problem in terms of X. We get 1.897 times 10 to the minus 3 molar. I'm going to check my 5% rule, which will pass by quite a bit. So my 5% rule is okay. And then I'm going to go ahead and solve for my pH by taking the negative log of that number and my percent dissociation, where I take how much hydrogen I have over the initial concentration times 100. I get 0.949% dissociation. Not very much. Then let's move on to the actual notes here. So now, find the pH and the percent dissociation of the acid, acetic acid, and it has some nacho in it, some sodium acetate. The Ka is still the same from the previous problem, which you'll need to have. Ka is still 1.8 times 10 to the minus fifth. So my major species now are HC2, H3O2, and I have this NaC2, H3O2. So notice there's always going to be parts that are similar. And I'll actually go ahead and get my highlighter out. So you can see I have this and I have this. In problems like this, we're going to have something where we have an alkali metal. It's almost always an alkali metal. I've never seen it really be anything else. And that's not going to be a part of our reaction. That's not going to be important. It's just there because we can't just have a jar of ions sitting there without some sort of cation, but it's not going to contribute to our problem. So choose the species that can dominate. Well, we only have one acid. This isn't an acid, so we're going to have our regular HC2, H3O2 becoming H plus C2, H3O2 minus. But notice that here I have this anion, and here I have that ion. And so we're going to see how this plays out in this problem. Find the initial concentrations of all the species involved. Well, I have my acid, and it's 0.2 molar, and I have my salt, which is really the C2H3O2 minus. I don't need that sodium. It's just there to help it get into solution, and that's 0.5 molar. I noticed that I started cutting out writing the equilibrium expression, and so we do need to go ahead and write that equilibrium expression. Let's see. Okay, get back up to where our problem was there. Okay, here's our problem. So we do need to write this equilibrium expression. Give me my pen back. So Ka is equal to H plus C2H3O2 minus over HC2H3O2. That looks like H7, but that right there is H plus. Okay, I went right ahead then to my ice chart. So I'm going to write my reaction again. HC2, H3O2 becomes H plus. This is my dominating reaction. I'll set up my ice chart. And here's where things are going to change. I know that my initial concentration of this is 0.2 molar. But I also know that because of that sodium acetate, I have an initial concentration of my anion of 0.5. I don't have any hydrogen initially. My change is still the same. I have to shift towards what I have nothing of, which means this is minus x plus x plus x. That's going to be the same. But now I have 0.200 minus x, x, and 0.500 plus x. My next step says to go ahead and check the 5% rule, but I haven't solved for anything yet, so I need to squeeze that in there. I really cut my steps down quite a bit, and so we need to make sure that we still do all of the things that we did before. So I'm going to go ahead and solve. I have 1.8 times 10 to the minus fifth as my K. Hydrogen, if I look at what hydrogen is, it's x. I need to substitute in here, so I have 0.500 plus x, and on my denominator I have 0.200 minus x. Still, we're not interested in quadratics, so we can't get rid of this x because nothing's being added or subtracted to it. We can get rid of both of those x's. Okay, so I'm going to multiply this by my 0.2, and then divide it by the 0.5, and end up with x is equal to 7.2 times 10 to the minus 6, which is also equal to my H plus. I'm going to check my 5% rule. So I'm going to take 0.05, and I'm still going to take it just of my same thing, my acid, 0.200 molar, and I end up with 1.0 times 10 to the minus 2. 1.0 times 10 to the minus 2 is greater than 7.2 times 10 to the minus 6. So my 5% rule check is okay. And so then finally, we're going to go down here and find our pH. My pH is equal to the negative log of 7.2 times 10 to the minus 6. So my pH is equal to 5.143, and my percent dissociation is equal to 7.2 times 10 to the minus 6 over that initial concentration of 0.2 times 100, which ends up being equal to 3.6 times 10 to the minus 3%, or to take it out of scientific notation, 0.0036%. So looking at both of those, we can see, if we go back to our other problem, or we compare it to just our acetic acid without having that information in it, that it is, in fact, much, much less. Back in our other problem, we had, let's see, let me do this here. So if I go back to my other problem here, I go back and see my one before, my pH here from the previous problem that we did quickly was 2.7 and a percent dissociation of 0.949, and then by adding that sodium acetate, or that nacho, my new percent dissociation is much less and my pH is much less acidic.